Topic 4 is going to be Newton's method for n-dimensional nonlinear problems. So now I'm going to consider functions, so I decided to call them capital F. And these are functions of n variables that have n outcomes. So you sort of think of it as a vector of n functions, and each one of those n functions takes the same n variables as inputs. And I still want to solve the problem f of x equals 0. But now, because f of x is a function that has n outputs, this 0 on the right-hand side is a vector of n zeros. So it's the 0 vector. And let's remember that the gradient of f is this n by n matrix. So in the first row, I just have the gradient for the first function, the first component of this function f, so I called that f1. Second row is the gradient for the second component, f2, and so on. So I can make a Taylor polynomial around the point xk, and it looks exactly the same way as it did for the one-dimensional one, except here I have a vector of values. Here I have an n by n matrix. And here I have a n by 1 matrix, so a column vector of the function inputs. And so I'm going to play around with this Taylor polynomial exactly the same way as I did when it was just a function of one variable. So I want to imagine that I am approximating a point f of xk plus 1, and that's where this function is going to be equal to 0. So that gives me this relationship here. So I'm trying to find this point k plus 1 so that my function is 0. But instead of doing that, I'm just using the linear approximation and finding out where that's equal to 0. And then I just want to solve this again for x plus 1. And so it ends up being a little bit more complicated this time, because this is a matrix now. I can't just divide by the matrix. But if it's non-singular, I can multiply by its inverse. So that's going to put the inverse of the matrix in front of this term. So if I move this to the other side of the equal sign, it becomes negative. And then I multiply it by the inverse, and that gets me just this guy. And then I'm going to move the xk also to this side of the equal sign. So I've isolated my point xk plus 1. And this is basically the same formula as I had for the one variable case, except now when I had one variable, I could just interpret multiplying by the inverse as dividing by the derivative. And then I need a stopping condition. So what I'm going to look at here is this is my updating step. So this is how much I'm changing my guess. If this actually did converge to the true value, so if I put in x star here, and x star here, I should already be at 0. So it shouldn't move at all. So at x star, this quantity should be 0. So my stopping condition is going to be, again, the problem is this is a vector, so I can't just say less than something. But what I can say is how long that vector is. So that's going to give me some idea of how far away I am from the thing that I'm trying to calculate. And when that improvement gets below a certain level that I'm going to call tau, so I need to pick some tolerance tau greater than 0, but generally you think of this as a very small number. When the size of my update gets below that level, that's going to be my stopping condition. It might not be the best idea for a stopping condition, but I need some condition to stop, and so this will be okay. And it's more complicated now, but you still have the quadratic convergence that you had for the univariate case once I'm close enough to the value x star. So the algorithm for using this to solve an n-dimensional optimization problem, an n-dimensional nonlinear problem, I still need a starting point, x0, and then I'm going to try and improve that starting point using these Newton iterations. So if the gradient is non-singular, then I can compute the next step. So from x0, I can find x1 just by updating according to this rule. But I see this inverse of a matrix here, and I don't like that. So to avoid computing the inverse of this matrix, what I'll do is take this, and this is a n by n matrix times a n by 1 matrix times a column vector. So I'm just going to look at this product and say, well, that's just going to be another column vector u. So n times n times 1. I take the outer dimensions. That's what the dimensions of the product is going to be. And so that gives me u is also n by 1. So it's a column vector of n with n entries. And then I'm going to multiply both sides by the gradient. So what I end up with is this gradient matrix times my unknown. And then here I have the gradient times its inverse. So that's the identity. So that's just going to be equal to the function evaluated at f of xk. And this is exactly the problem that we looked at in the linear algebra section. This is a times x equals b. So this is something that we know how to solve. So the algorithm that I'll end up using to compute the n-dimensional Newton's method, so I have a tolerance tau greater than 0 and a starting point x0. And so for the kth step, I have to compute this vector f of xk, but this is just a vector of numbers now. And I have to compute the gradient. So I have a formula for the gradient, and I plug in xk. And so that's going to give me a matrix. So it's just a matrix of numbers now. So then I can solve this linear system and find the value u. And that value u is the size of the update that I want to use in my Newton iterations. So I'll update. So my current guess is xk. I update that by subtracting this vector u that I got by solving this linear system in step 2. And that's going to give me xk plus 1. And then if the size of this u is less than tau, then I'm going to return xk plus 1 as the answer. Otherwise, I'm going to go back to step 1 and just pretend now that this xk, once I'm on the next step, that's going to just run me through this same set of steps again. So I'll do a very simple example. So if I take 1 minus, so this is x minus 1 to the 4th power and y minus 1 to the 4th power. So these are both going to be positive. So when I subtract them, they're both going to be negative. So it should be pretty clear that this is going to have a maximum when this is equal to 0 and this is equal to 0, and that maximum is going to be equal to 1. Because if I put in anything non-zero for these, it's going to be subtracted from 1, so it's going to make it smaller. So this should have a critical point at the point 1, 1. Or it has a maximum at the point 1, 1, so it should have a critical point at the point 1, 1. So I can compute the gradient of this. So this is the gradient of the function that I'm trying to find the critical point of. So this is a function, it's a function of two variables, but it's a scalar valued function. When I evaluate this, I just get a single number. But when I want to find a critical point, what I want to find is a point where the gradient is equal to 0. So now the gradient is my function of two variables. And this is what I want to use Newton's method on. So I want to use Newton's method to find the point where the gradient, so basically where the derivative is equal to 0. And you have to be a little bit careful here because in general, when you think of a function that has several outputs, you think of that as a column vector. The gradient here is a row vector, so I've just taken the transpose here and the transpose here so that everything lines up the way it should. The gradient of f of x, then, is just this function, so it has a very simple gradient. And now I'm going to use R to run through several iterations of Newton's method to try and find the solution for this. So the pieces that I'm going to need to be able to do this, I need a function that I'm going to call capital F, and this is going to evaluate the function that I'm trying to find, that I'm trying to make equal to 0. So this is a pretty simple function. It's just going to be, so it has two inputs and two outputs. The first output is just 4 times x minus 1 cubed, so it's basically just returning the gradient of the function that I'm trying to find the maximum of. df is going to return the gradient of f. So those are just this and this, but written out in R form. So what I've done here is I've looked at the diagonal elements. This is the top left element. This is the bottom right element. And I've put them in a vector. And then a shortcut for making a diagonal matrix is just to use this function diag. If I give it a vector as its argument, it makes a diagonal matrix that has these elements down the main diagonal. And then I don't have a particularly good way of choosing a starting point because it was pretty clear from the definition of the function that the point I'm looking for was 1, 1. But it won't be very exciting if I choose that. So another commonly chosen starting point is 0. So I'm going to start at the 0 vector. So I'll say x is equal to 0, or assign the 0 vector to the variable x. And then I'll do 25 Newton iterations. So because I've defined these functions as functions of x and y, I need to provide each one of them with two arguments. So it's just the first element of x and the second element of x. I can use the solve function to solve the linear system that I was talking about on the previous slide. And so all I have to do is give the matrix A and the vector B, and solve is going to solve that linear system for me. And then my updating step is just to say xk minus u becomes xk plus 1. And so when I run this code in R, it's going to take xk, it's going to subtract the vector u, and then it's going to write the answer to that into the same piece of memory that I originally was using to hold x. And then I'm going to put that in something called a for loop, which is just going to run this line 25 times in a row. And so we can look at x after this has gone 25 times. So x started out as 0, 0. And then after 25 Newton iterations, I end up with 0.9999 and 0.9999. So it's gotten very close to the point that I was looking for, 1, with these 25 iterations.